Welcome to qnawire.
So for problem 122, we're asked to find the centroid of a hemisphere's halves, where we have 1/2 a over 2, and the other half a over 2, where a would be the total height of the hemisphere in the x direction, or length. And so we're asked to find the center of gravity of both of those components, component 1 and 2. And we'll do that by integrating over a small sliver, a disk, really, and integrating that through each half of the hemisphere, using this equation where the centroid times the entire volume of each component is equal to the sum of the centroid of the element, or the disk, that is being integrated, or instead of a sum, I mean an integral of the centroid of each element times the change in volume for that element. And so we'll start off with component 1, and we'll find the volume that we need for the left side of the equation, which is equal to the integral of the change in volume over each element. And dV is equal to pi r squared, so we take a circle and multiply it by the change in x value, and that'll give us the elemental disk. So the volume is going to be equal to the integral of pi r squared dx. But we want it in terms that we know. We don't know the radius, but we can use a, the total length of the hemisphere. And so knowing that the equation for a circle is going to be x squared plus y squared, and the hemisphere follows the curve of a circle, is going to be equal to a squared. And y is just going to be the radius. It's going to be equivalent to the radius because that's in the same direction. So r squared is equal to a squared minus x squared. And now we can plug that in, so we have it in terms of a, which we know. We're integrating from 0 to a over 2 because we're just doing the first component, or half of the hemisphere. And that comes out to pi times a squared x minus x cubed over 3 from 0 to a over 2. So the volume of the first component is 11 over 24 times pi times a cubed. Now let's find the right side of the equation. Which will be equal to the integral from 0 to a over 2 x, which is our differential element, the disk that we're integrating, times pi a squared minus x squared. We're just plugging in dv here. And this comes out to pi a squared times x squared over 2 minus x to the 4th over 4 from 0 to a over 2. Simplified further, that's equal to 7 over 64 times pi a to the 4th. Now we know everything we need to find the centroid. So going back to this equation, we found the volume, which we can plug in now as 11 over 24 pi a cubed, and set it equal to the right side of the equation, which we solve for as 7 over 64 pi a to the 4th. And we get that the centroid of component 1 is equal to 21 over 88 times a, the length of the height of the hemisphere, or length, depending on which way you look at it. Now we can use the same method to find the centroid of the second component. So the volume of the second component this time goes from a over 2 to the full length of the hemisphere A. We can plug in dv that we found earlier. We get pi times a squared x minus x cubed over 3 from 0, from a over 2 to a. And we get the volume of the second component is 5/24 pi a cubed. And now we need to find the right side of the equation again, where we have the integral of the differential element times the change in volume. Is equal to the integral from a over 2 to a of our differential element, which I'll just simplify to x. And we can plug in dv again. Simplifying, we get pi times a squared over 2 minus a to the 4th over 4 minus a squared a over 2 squared over 2 minus a over 2 to the 4th over 4. And so this works out to be 9 over 64 pi a to the 4th. And now we can solve for the centroid of the second component. We just found the volume to be 5 over 24 pi a cubed. And we just found the right side of the equation as well. So plugging those in, we can now solve for the centroid of the second component. We get 27